Good evening, everybody, and welcome to Astronomy Off Tap Edinburgh, May 2021 edition. For anybody who hasn't joined us before for any of these events, Astronomy on Tap is a free event that's run by volunteers that features accessible, engaging science presentations on a range of topics from planets to black holes to galaxies to the beginning of the universe. First Astronomy on Tap event was started in New York a few years back and has spread around the world. Obviously, due to the pandemic, we would usually be in a nice warm pub in Edinburgh. Unfortunately, obviously, we're not allowed to do that at the minute, so we have coming to you live on YouTube. And this is our 13th now off-tap event and our 35th overall. If anybody is interested in learning about future events, please do subscribe to our YouTube channel, or you can follow us on Twitter and Facebook. You'll see them just down here. So welcome to Astronomy Off Tap Edinburgh. Tonight, we're very lucky to have a couple of fantastic speakers from the world of astronomy. We'll also have our usual updates on rocket launches for this month and some games, of course, to get involved with. The Astronomy on Tap crowd always has some great questions, so please do get involved. If you do have any questions for our speakers, please do comment on YouTube. You can also post them on Facebook and on Twitter as well. So please do let us know if you have any questions. So to get us started for the evening, I'm going to hand over to our resident rocket expert, Fred, who's going to give us a bit of an update on what's happening this month in the night sky. So Fred, over to you.
Hi, thanks for that. I will share my screen. Okay, can you see that?
Yeah, that looks great, Fred.
Fantastic. Right. So, yeah, there's not very many rocket launches this month, but there's a nice little surprise at the end of this presentation, and it's quite cool. Right. So the first launch is a Falcon 9, which is going to be launching Starlink 27 for the SpaceX's Starlink broadband system. And the booster that's actually being used, it's 10th time this one's being used. That's pretty awesome. Next up, 27th of May, you have a Soyuz that's taking some OneWeb 7 constellations into space as well. And this is the 67th launch of that Soyuz model. And then there's a few things, but the dates haven't been confirmed yet. So India's launching a geosynchronous satellite. Yeah, and it's going to be its first GEO imaging satellite. And the cool thing I was talking about was China's landing a rover on Mars. So Perseverance is going to have a buddy. And then there's a Chinese Long March 7 launching the resupply for the future Chinese space station. Thank you. Short but sweet.
Thanks so much, Fred. That's fantastic. Okay, so moving swiftly on to our first speaker of the night. So we're very lucky to have with us Dr. Yan-Chuan Cai, who is currently at the University of Edinburgh. So Dr. Cai got his PhD at Durham University back in 2009 and has also previously held postdoctoral research positions at the University of Pennsylvania, Durham University as well, and the University of Edinburgh. And currently, he is a Royal Society University Research Fellow at the University of Edinburgh, so local to us, which is fantastic. His research activities are in cosmology, especially looking at the large-scale structure of the universe, the cosmic web, and dark energy. And tonight, he is going to be talking about intergalactic filaments and their spinning. So Cai, I will turn my screen off, and I will hand over to you.
Right, thank you, John. Can you guys hear and see me?
Yeah, coming across loud and clear.
Thank you. I'll start to share my screen. Thank you for being here at this beautiful evening, at least in Edinburgh. Broadcasting from a flat near the Royal Observatory of Edinburgh. It's live, and it locates at the north part of our planet Earth, and which is part of our solar system. And as part of the context, our solar system, of course, is one out of the hundreds of billions of stars in our Milky Way, which itself is only one out of the hundreds and billions of galaxies in our universe. Right, so the story I'm going to tell you, to share with you, is our quest about the possible spin of intergalactic filaments. So this is almost like a primitive curiosity-driven question. If you go and ask my 6-year-old son about the solar system, he will probably tell you that we know that most of the planets are really spinning, and they're also orbiting around the sun. So
sorry, Chai, I don't think we can't see your slides. I'm not sure if you shared them up or not.
Oh.
Sorry to interrupt you. I apologize.
Right.
I wasn't sure if you were sharing your screen with your slides. We couldn't see anything coming up.
Okay, let me see. Indeed. Can you now see my slide?
Not yet. We can see you, but I can't see any slides coming up. I think if you click share screen at the bottom, oh, something's starting. There we go. Yep, that's come up. Brilliant.
Okay, apologize. I think some technical issue. Right. So moving on from the title. So the story is about our recent research activity on the topic of the possible spin on intergalactic filaments. So let's start from our solar system. As probably most of us know that most of the planets in our solar system are spinning themselves, and they're also orbiting around the sun. And in particular, on the planet Earth, its spin gives us day and night, so its period is essentially a day. And it's also rotating around the sun at around 30 kilometers per second. So in 1 second, it goes 30 kilometers. And it's this whole period of an orbit, gives us a whole year. That gives us the calendar. So further, if we look outside of our solar system, we realize that we are just one of the many hundreds of billions of stars in our Milky Way, and it sits around this part of the spiral arm in our Milky Way. And the sun itself is also spinning, actually. It takes around 25 days at the equator of the sun to go around one orbit. And then the sun itself is also orbiting around the center of the Milky Way. And we can work out the period of this. It takes around 230 million years to complete an orbit. And this sometimes is called a galactic year. And for those of you who have really good memory, you probably would remember what it was like in our planet Earth in the previous galactic year. And that was the era of dinosaurs. Right? So it's probably a coincidence, but yeah, the previous galactic year is the era of dinosaurs in our planet Earth. So look further outside, let's zoom out, we realize that our Milky Way system, together with M31, is only a small dot in this local supercluster. It was only recently named the Yan-Chuan Cai by this group of researchers. So you can start to see some pattern here that there's a web-like structure much further beyond the local galaxy and the local group of galaxy. And if we look further outside, then this is the so-called large-scale structure of our universe. So you can see each of these dots, essentially you can think of it as represents a galaxy. And there's hundreds of thousands of galaxies here where they form this cosmic web structure. There are large empty void regions, and there are clusters of galaxies, and there are filamentary kind of structures, typically connecting some clusters of galaxies. So the natural question to ask is, we know that our galaxy is spinning. We know that also galaxy of clusters are spinning, whether these filamentary structures themselves spin at all. So to answer this question, it's not very straightforward. We turn to use cosmological simulations. So with our knowledge of how our universe form and evolve, we can teach our supercomputers to evolve the matter distribution of a decent chunk of the volume of the universe. And this is what it looks like if we were able to see the matter distribution of the universe, which actually is dominated by this substance called dark matter. So, but you can see these bright dots around this web structure here. These represents the locations where potentially a cluster of galaxies would form, and each of these bright dots are likely to form some galaxies. But it's also empty void regions here and filament structures that typically connecting pairs of these potentially galaxies. So just to show you how realistic these simulations are, here's a little test for you. I'm showing half of this chunk represents the real observation, and the other half represents the result coming out from the computer simulation. It will be challenging probably for people who don't know the subject to tell apart which part is coming from real observation, which part comes from computer simulation. So let me just show them the answer here. On this corner here, they are coming from these real observations from the so-called 2DF Galaxy Redshift survey, and also some other surveys here. Each dot essentially also represents a galaxy. So this is really the cosmic web structure revealed by our large surveys using telescopes. And on the lower corner here is the results coming from computer simulations, trying to mimic what the universe may look like. So then, remember our question is to see if some of these filamentary structures that connect big blobs of galaxies are spinning or not. And to look at, to give you a intuitive impression, let's look at one of the examples from simulation. Hopefully you can see this, start to see this movie. Here it shows a filament that we picked from the simulation. And each of these dots represents the flow of matter towards the filament. And also, as you can see, these streaming motions of this matter, actually there's channeling towards these big bright orange points, where that's potentially where a so-called dark matter halo will form, or dark matter clumps will form, and that's potentially where the galaxy cluster or galaxy will form. So you can see this motion of matter are primarily dominated by this streaming motion towards the cluster, but also you can see some of them are actually coming perpendicular to the direction of the filaments. So these are, it looks like there's potentially some weak rotational motion for the matter flow towards the filament, and that's the called tentative phenomenon, or the signal that we're after. So with a simulation, a computer simulation like this, we can look at sections of filaments by identify this pair of bright objects, essentially that would represent pair of galaxies. And you can see, as guided by these boxes here, lots of them are likely to be connected by a filamentary structure. And we know that the tentative signal, the rotation of filaments are likely to be quite weak. So to visualize them better, we need to average many of these filaments together. And that's what we did. So here shows the average of a few hundreds of thousands of filaments together. the colors here shows the matter distribution across the filament. As you can see, this is labeled here. This is potentially one of the simulated galaxy, location of the simulated galaxy, and here's another one. And in between, they are indeed connected by a high density of matter. So that's kind of the average filament signal. But then on top of that, there's also these arrows that shows you the velocity of the filaments. It's actually, this filament is being sliced from the middle. So to show you what this represents, essentially, and use this gadget to demonstrate. So essentially, the filament is going this way, and these two knots here represents two galaxies, and in the middle, the green is to represent the filament. So it's going around in this way, on average. So yeah, essentially, if from that review, the so-called angular momentum, which characterize the rotational velocities pointing from the left to the right. So as you can see, the typical length of these filaments connecting the pair of galaxies is around tens of millions of light years long. And this is just give you another view. Now we are seeing the filament essentially along the direction of your screen. So it's slicing it across. So you can see more obviously the kind of rotational velocities around the center of this cross-section of the filament. So there's a clear rotational velocity, maybe more obviously seen in this way. So as for how long these objects typically are, as I've kind of shown you, they are typically tens of millions of light years across, possibly the longest spinning objects in our universe, if it's confirmed. So we can also work out from using these simulations with all the velocity information available, we can work out how fast these things are spinning. So it's typically around order of 10 to 100 kilometers per second. So if we were to make some new terminology, as mimicking the galactic year, we make some, we call them filamentary year. We can work out roughly, on average, how long a filamentary year would be. And it turns out that on average, they could be as long as the age of the universe, which is close to 14 billion years. So unfortunately, for the filament to rotate, to complete one orbit, it could take as long as the age of the universe. So just to briefly wrap up, so I've shown you the picture of the cosmic web, and typically there are filamentary structures around a connecting pair of galaxies, and these are typically tens of millions of light years long, and they're likely to spin at around tens to hundreds of kilometers per second. And a filamentary year could be as long as the age of the universe. And this thing is quite relatively weak. The signal is relatively weak, as we anticipate from the simulation. It's possibly going to be quite challenging to observe, but it's not impossible. In fact, this is a story still developing. I can show you some preliminary results from another group of people who has conducted an observational analysis, and this is coming from real data, and they seem to have found a clear detection of this filament rotation signal. So this is showing again the average of many of the filamentary structures from the Sloan Digital Sky Survey, I believe. And we're again seeing the average filament on the horizontal direction. On the upper part, essentially, things are moving away from us. On the lower part, it's moving towards us. So this is kind of a clear signature of a rotational system. Finally, let me finish by showing the team that we collaborate to conduct this work. So there's a few of us, essentially. Well, there's another PhD student, Jenny Xia from University of Edinburgh, and also Mark and Miguel. We work together over a substantial period during the lockdown. And this further read, the paper is on the archive, and also last June, during the pandemic, actually, there's still some interest coming from new scientists to cover our story. So if you're interested, you can take a further read about it. I think I'll stop here and take questions. Thank you.
Thank you so much, Chai. That was a really, really interesting talk. Thank you so much for coming along and giving that to us. We do have a few questions for you, if that's okay with you.
Sure.
Okay, great. Okay, so the first question we have is, can we make any sort of assumptions about dark matter by looking at these filaments and how they spin? Can we make any assumptions about what's not there by looking at these?
That's a really good question. Actually, there's one of the collaborators, Mark, he's been actually advocating to use this spin of the filaments as a probe to possibly distinguish the nature of dark matter. So there has been proposals about dark matter being possibly coming from some elementary particle. They essentially it's a wavy behavior. It's coming from the quantum behavior, and those sort of dark matter candidates would probably give you a different feature in terms of the filamentary. The rotation of the filaments, and that could potentially allow us to distinguish that kind of dark matter versus the normal. We normally will assume them to be the so-called cold dark matter. Or axion is the one that I was looking the term I was looking for. Yeah.
Fantastic. And then another question we have was, what telescopes are used for the surveys that you showed?
So the examples that I shown, I believe, is combination of several. There's AAT located in Australia that conduct this 2DF galaxy redshift survey, and there's CFA survey of the Great Wall. That's much earlier. Can't remember exactly. It's probably somewhere from Hawaii. But it's a combination of several. But now, actually, this is slightly out of date. There are bigger surveys. There's Longitudinal Sky survey that goes much further beyond this.
Fantastic. And then sort of slightly related, I guess, to how these are being monitored and how you're able to see these through the telescopes that you're using. But what kind of matter are the filaments made up from? And so the assumption is that the early universe, that they're mostly hydrogen atoms, right? So how are they visible?
That's a good question. So that's related to our standard model of cosmology, which essentially is well supported by various observations. Now, in terms of matter in our universe, we now know that the ordinary matter that made up of the gas and the stars and galaxies accounts for only 4 to 5%. Of the total matter energy density of the universe. And then there's around 25% of the matter, they are totally dark, in a sense that we can't see them emit any lights, and we can only detect them mostly through gravitational interaction. So essentially the visible matter versus the dark matter ratio is about 1 to 5. So this picture that is shown coming from cosmological simulations are essentially representing the total matter, but predominantly it's just dark matter. And But then the hypothesis, and also again well supported by observation, is that at the locations where there's concentration of dark matter, like these clumps of matter here, that's where there's host the growth of galaxies and clusters of galaxies. So essentially, all these bright dots in this cosmic web can be seen as the locations where the galaxy is going to grow. So in the observation, the tentative observational result that I've shown you, they essentially use galaxies as tracers of the entire matter distribution, essentially. So the distribution of galaxies in this cosmic web essentially is like a tips of iceberg, where the ice, the under the surface of the water is the major chunk of dark matter, but you can use the galaxies as your trace of the entire matter distribution in our universe, and that's what the observers do. That's why we use big telescope to survey many of the galaxies, put them together, and they look incredibly similar to the cosmic web structure that we see in computer simulations.
Fantastic, thank you. Okay, we just have two more. There's lots of questions coming in. There's lots of interest in your talk, which is great. But are there any particular consequences for these either spinning or not spinning?
That's again a very professional question. So in fact, there has been a lot of studies on the spin of these filaments may have some connection with the spin of the galaxies inside the filaments. So these are massive systems. Between these two major pair of the galaxies, there are potentially many galaxies exist between them. So in both simulation and observation, people have found that the rotation, the spin of those galaxies along the filaments, actually, especially the spiral ones, they tend to align on the direction of the filaments. So there's some connection between the spin of galaxies in the filaments. So that's one thing that's kind of related. You can use the spin of this filament as perhaps an additional way to explain the spin of the galaxies in them. And maybe more speculative, this could be a mechanism for boosting or generating magnetic fields at these massive scales, because the late-time universe is largely ionized, as these are full of free electrons and they are spinning. So this is kind of a dynamo system.
Fantastic. And then our final question for you comes from YouTube, and they said, if a filamentary year is the age of the universe, could it be modeled in reverse to study the simulation of the early universe?
That's a good question. I think these are at the moment still sort of qualitative. We have kind of order of magnitude estimates for the average period for the spin of this stuff, but I'm just showing you a backup slide where this is the full distribution for the period of the filaments individually from the system compared to the age of the universe. So you can see they have a broad distribution. It just happened to be that the average turns out to be close to 1 times the age of the universe, but depends on the selection of the filaments, the definition. This could vary. I think the precision, the precise definition of these objects is probably not good enough to allow us to reverse engineer to set constraint on cosmology yet, but it is possible.
Fantastic. Well, thank you so much, Chai, for that really fascinating talk. We really appreciate you coming to join us tonight. So thank you very much indeed.
Thank you, and thank you for all the questions.
No worries. Okay, so if I could ask you just to unshare your screen, and then I shall pass over to, it's our midpoint of the event tonight. So I'm going to pass over to our games master for this evening, over to Becky, for our midway game. So Becky, I shall hand over to you.
Oh, I'll just share my screen. So the game this week, for those who haven't done it before, is a constellation unscramble. So we have a series of these are all constellations, and your task is to rearrange the letters to form names of constellations from these, and then once you have an answer, to put it onto our message, tag us on Twitter or put it on Facebook, or however you send it by carrier pigeon. Send our answer to us and we'll see how it goes. So I'll leave this up here for people to look at, and yeah. Okay, so I hope you've all had a look at that and had a chance to refill your drinks. I'll pass back over. This will be on our social media, so it'll be on Twitter for you to, if you haven't had a chance to have a look at it, it'll be on Twitter for you to keep looking at. And I'll pass back over to John for to introduce our next speaker. Thank you very much.
Fantastic, Becky. Thank you so much. I just spent about 3 minutes staring at those and trying desperately to unscramble my brain enough to do those, but those were hard. They were very, very good. Remember, if you do have the answer, as Becky said, please do post it on YouTube, stick it on Facebook, on Twitter, and carrier pigeon, just as Becky said. So whatever form of communication you have available to you, to use those. If you get it, you're better than me. So that was a good one. Thank you, Becky. Okay, so we now move on to our second speaker of the evening, which is Dr. Andrew Williamson. So Dr. Williamson is a born and raised Edinburgher. I think I've lived in Edinburgh enough to call it in Edinburgh. Since beginning his PhD in 2012, he's been involved in gravitational wave research within the LIGO and Virgo collaborations. He is currently a postdoctoral fellow at the Institute of Cosmology and Gravitation at the University of Portsmouth. And so we are having him here tonight to talk about gravitational waves. We're very lucky to have him. So, Andrew, I will pass over to you for your talk. Thank you ever so much.
Thank you, John. Thanks for inviting me. I'll share my screen now. So I hope you can all see that. So yes, thanks very much for inviting me. I'm based at the Institute of Cosmology and Gravitation at the University of Portsmouth. And I'm going to talk to you tonight about gravitational waves, give you sort of a little primer on what they are and some of the things that we're learning by doing gravitational wave astronomy, which is still a relatively new field in astronomy. So I'm going to begin with a sound. And this sound is the first ever detection of gravitational waves. So I hope you could all hear that. There was a distinct beat, a pulse. You heard it 4 times. Did you hear it?
I don't think we could quite hear that, Andrew. No, it didn't
No.
come through, unfortunately, no.
Oh, that's a shame.
It came through well in the test, didn't it? But yeah, we didn't quite
did.
hear it that time.
I know what I can do. I can crank the volume up on the presentation and then give it another go. How about that? No?
No, unfortunately, it didn't come through. If you do the share again, it might come through that way. That might
It might come through because it did this the first time. If I do share again. If not, it's not the end of the world, but let's see. Did you hear it?
Oh no, unfortunately not. It's not coming through.
Okay, never mind.
It's the tech goblins at work, unfortunately.
Yep, it works the first time and then not the second time. Never mind. Well, anyway, we'll have plenty more to talk about. So, just before I begin, I'm part of this LIGO scientific collaboration, which is a very large collaboration with people at many, many institutions all over the world. The UK contingent is mostly shown over here, including University of West of Scotland, University of Strathclyde and University of Glasgow as the Scottish groups. There are thousands of scientists actively involved in this collaboration, but so the results that I'll talk about are from the work of these collaborations, although tonight I'm speaking in my personal capacity, so if I give any opinions, it's not on behalf of all these other colleagues. So to begin with, let's think about what gravity is before we get to gravitational waves. So over 100 years ago now, Albert Einstein published the theory of gravity, which is called the general theory of relativity. And in that theory, we actually come to understand gravity as being the impact that matter has on something called space-time. And space-time in this illustration is shown by this green grid. And you see.
Oh, sorry to interrupt, Andrew. I think we're not seeing your slides. I can see the front slide, but I can't see the. Oh, there you go. Yeah, that's coming up now.
So if I do this, can you see the?
I can see the slide. Yeah, I can see the gravity according to Einstein. Yeah,
okay.
That works. Sorry.
Great. No, it's typical. All right. So what you see is this grid here, which is space-time in a cartoon form, and the sun and the Earth here are making dents. They're warping space-time around them, and the sun is more massive than the Earth, so it makes more of a divot in the space-time. It warps space-time around it more than the Earth does, and that is why the Earth orbits the sun, because it is moving through a curved space-time, and this is gravity according to Einstein. So we've got a little cartoon there of a planet swirling around in this curved space-time. So if you think about orbiting planets going around stars, or indeed the sun going around the Milky Way, it's because of great amounts of matter bending space around it. And basically the theory can be summed up nicely in the phrase, space-time tells matter how to move and matter tells space-time how to curve. So that's the relationship. Now, if you go beyond static objects and you think about how things interact with space-time when they move, well then you can imagine two objects swirling around one another, creating ripples in the space-time, as shown in this cartoon. And these ripples are gravitational waves. So when you have objects, in this case perhaps two stars, swirling around each other, they can produce ripples that move outwards at the speed of light and carry information to us if we are waiting to pick them up. So if you want a recipe for making strong gravitational waves that we can detect with our instruments that we have at the moment, really you want two massive objects, and by massive I mean, you know, like the weight of stars or many stars, and the denser the better. And that is because the more dense that matter is, the closer these objects can get to one another, the faster they are able to orbit one another, and so the more powerful the gravitational waves are that they can generate. And so if you have these two objects orbiting around one another, eventually they will give off gravitational waves, their orbits will shrink, and they will gradually spiral and spiral closer and closer together until eventually they collide. Now, what kind of objects might we be thinking about here? Well, on the top here, we've got small stars, and that's stars like our own sun. As they live their lives and get to old age, they'll swell to be red giants. And when they die, what will be left behind is something called a white dwarf. Now, a white dwarf is sort of like the size of a planet. And for us, that's too big. It might be the right kind of mass, but it's too big. So that's not really very useful for gravitational wave production that we can detect at the moment. In the future, yes, but with our detectors that we have, it's not really an option. The things that we are really able to detect are from larger stars. So we have some stars which are more than, say, about 8 times the mass of our sun, and they will end their lives in a supernova explosion. And if the star is between about 8 and 20 times the mass of the sun, this supernova will involve the core of the star collapsing down under gravity to form something called a neutron star. And this neutron star is like an extremely dense ball of material, which has many exotic properties. And these are kind of key culprits for us if we're hunting gravitational waves. If the star is more than perhaps about 20 times the mass of the sun, then when it undergoes a supernova explosion, the core is so massive that even the forces that hold a neutron star up will not be able to counteract the gravity that this enormous core is producing. And the whole thing will just collapse down and form a black hole. And these are the kinds of objects that we are really interested in here. So let's look at black holes. Just a little summary, black holes are regions of space-time where gravity becomes overwhelmingly strong. Nothing that goes inside the event horizon of a black hole can ever come back out, or no information inside there can reach us. So black holes are shrouded by this surface, which is really just a boundary in space-time around them, at the points at which gravity becomes overwhelmingly strong. Now this image is now quite famous. Many of you may have seen it. It's the supermassive black hole sitting at the center of a galaxy called M87. And this shadow here is a shadow being cast by the black hole, which itself is about 6.5 billion times the mass of our sun. And the glowing emission that you see is from hot material that's orbiting around this black hole and giving off lots of emission and light because it's very hot. And the black hole is sitting there in the middle and casting a shadow. And to give you a sense of scale, what you can see there, the circle is the orbit of Pluto. So the whole solar system would neatly fit in that shadow region. So this is a very large black hole, but we also see black holes that are more like the mass of stars. So they're called stellar mass black holes. And those are the ones that we can, at the moment, see with gravitational waves. And then onto neutron stars. Well,
Sorry to interrupt you, Andrew. I think we've got a bit stuck on the slide thing again. Could you stop it and start it again? Is that all right?
Yeah.
Sorry, this is this typical technology. I can see Messier 807. Yeah, I can see M87 there. I think it's when you click play, it's not clicking through. So that might be why.
So what was the last slide that you?
So we were stuck on the. That's come up now. Yeah, the M87 one's come up now, but I think it's difficult when you go through it. Yeah, so this one's on there now. Yeah.
And then do you see black holes now with M87
yes.
again? You do.
Yeah.
Okay. I'll
Sorry, Andy. Sorry to interrupt. I know it's not easy for the talk when I interrupt like that. But
it's fine. It's fine. I think maybe it's the controller I'm using. I don't know. So I'm just going to click the keyboard.
Okay. Thanks.
So yeah, as I said, you can see how the solar system fits inside the shadow of the black hole there. So that gives you a sense of scale. So that's a supermassive black hole, but what we are interested in are stellar mass black holes, which are more like the mass of the sun, or maybe tens to a few hundred times the mass of the sun. Now on to neutron stars. So this is another new slide I hope you can see.
That one's not coming up, so you might want to try. Yeah, sorry.
Okay.
Yes, there we go. Strange. It's up. No, it's probably the space gremlins in the system for tonight. I'm not sure why, but I can see the neutron star. That's coming up now.
Okay. So here we have a 2-scale illustration of a neutron star. It would not quite fit inside the city bypass, but it's not far off. They'll have masses between about 1 and 2 times the mass of the sun, but be only about 20 kilometers across. So they're incredibly dense, and the matter inside is many times more dense than in the cores of atoms. And actually, we're not able to produce material like that in any laboratory. So if we want to understand how matter behaves when it's extremely dense and there's lots of strong magnetic fields around, then really we have to study neutron stars. And that's one reason why gravitational waves are very, very valuable. So going back to this illustration, can you see the ripples?
Not yet.
Okay.
Yep, there you go.
Maybe I should just leave it in this view and maybe it'll work. So we've got the ripples. Now, how do they have an effect that we can measure? Okay, because like a ripple in space-time, you think, what is that and what does it do to us? Well, Albert Einstein is currently having a rough time of it because a gravitational wave is hitting him square in the face, and you can see that he's being stretched in one direction and compressed in the other direction at the same time, and that oscillates back and forth, and that's the wave oscillation. Now, this is obviously very exaggerated. We don't experience this, thank goodness. But when a real gravitational wave passes by, the same kind of effect is happening. It's just that it's at a scale much, much smaller than the size of an atomic nucleus, perhaps about 1/1000th the width of a proton. So that's the task that we have at hand if we want to measure this effect. So this is an animation of the detectors. So what we have here is a laser, and we're shining it at a special mirror, which splits it into 2. And at the ends, the light was going up and bouncing off 2 mirrors. Now, if we build this instrument so that these arms are the same length, and we shine the laser up, then when the light comes back and joins together, it will interfere with itself in a way that this detector here will see no output. It will just cancel out. But then when a gravitational wave goes past and changes the distances and makes them different, then you can get interference that isn't destructive, but they can add together. And our sensor at the output will register a pattern of bright and dark. And this is how a gravitational wave interacts with our detectors and how we're able to actually measure such a tiny effect coming from from deep space. And what you see here are some of these instruments that we've built. 3 of these are photographs of the LIGO detector in the high desert of Washington in the west of the USA. This is the LIGO Livingston detector in Louisiana. And both of these are 4 kilometers long on a side. The laser goes along a 4-kilometer long tube, bounces off a mirror and comes back. The Virgo detector in Italy is the same kind of idea, but it's slightly smaller at 3 kilometers. And there is recently, adding to the list, there's a detector called Kagra in Japan. And that's actually built under a mountain where there's an old mining complex. And that's also 3 kilometers long. So these are the primary instruments that we have been using and will continue to use to do gravitational waves for the foreseeable future. Now, this was the thing with sound, which perhaps you can't hear.
Oh no, we can hear that. That's coming through perfectly.
Right, you can hear it now. Okay, well, I'll explain it then. What you were hearing there was the first detection of gravitational waves coming from a pair of black holes, and you saw the illustration. It was going left to right, so that's in time. And what we've done is we've just converted the signals straight into audio. The first time when it was a deeper sound, that was really basically unaltered. Then when it was a higher whipping sound, that was just the same signal, but with the frequency put up so that it's a bit more friendly to the human ear. And so this is a characteristic type of signal where you can see that the wiggles get bigger in amplitude and also closer to one another. So there's an increase in frequency and amplitude, and then it peaks and dies away. And we call this a chirp. And this was seen with both of the LIGO detectors in 2015 and was confirmed as the first detection coming from a pair of black holes. And it's quite amazing that you can just play it as a sound file. Now, we've since seen many other detections. We've got about 50 now. And they go from the most massive one up here, which you can see is a slow wiggle peaking around here, down to least massive. And the less massive systems, they have many more wiggles, many more cycles of the wave before the merge event happens. So we've got many, many pairs of black holes, but down here, the bottom one, this is actually a pair of neutron stars. So we've seen black holes and neutron stars now involved in these merging pairs. So it's very exciting, and as we go into the future, we should see many more. So this will be the last slide that I'll show. This is the same set of detections shown in a different way. What we have is in the vertical direction, we've got the mass of the objects involved from 1 times the mass of the sun up to 160 at this line. And I've circled 2 events. You can see that most of the blue ones are black holes that we've seen merging with LIGO and Virgo, which lie between about 20 and 40 times the mass of the sun. But there was this one event which had one of the black holes more than 80 times the mass of the sun, and it merged with another to form a black hole that was about 150 times the mass of the sun. Now this black hole at about 85 times the mass of the sun, this is a challenge to astrophysics, because we think that above something like 65 times the mass of the sun, a star might struggle to actually be able to form a black hole when it dies, because there's a kind of instability that occurs. And when the core collapses down, this instability actually leads to a thermonuclear explosion, and the whole star basically obliterates. And so it doesn't even leave a black hole behind. The whole thing just blows up. So how did we get a black hole that was about 85 times the mass of the sun? Could it be formed in a star and we've misunderstood something? Or perhaps maybe it itself was the product of a merger in the past. So what we might have seen is a kind of second merging event in a chain. So that's an interesting event. And then this other one here, where you see a black hole merging with a very small object to make a slightly larger black hole. This object is a challenge because it lies at a mass about kind of 2.6 times the mass of the sun, which we think is a little bit too big to be a neutron star. So we think the biggest neutron stars can probably only be two and a bit times the mass of the sun. This one is maybe a little bit too big. But at the same time, we don't really see many black holes in gravitational waves or with any other methods. The purple ones have been observed with other telescopes. We don't really see many of them below about 5 times the mass of the sun. And so there's been this gap between the smallest black holes and the largest neutron stars. And the question here is that, is this object a black hole? And it suggests that actually black holes do exist that are in between, but maybe we've just not been able to see them yet. Or could it have been a neutron star, and maybe neutron stars can be bigger than we thought? In terms of on balance of probability, it was probably a black hole, but it's still there's some space for interpretation there for that object. So those are just two, and I can't obviously go into any more. I'm out of time, but two of the objects that really push our understanding at the higher mass end and the lower mass end of how black holes and neutron stars are, how they behave, and how they form and merge. So I'll stop there, but thanks very much for listening.
Thank you so much, Andrew. That was a really, really interesting talk. I'm sorry for the technical problems, but I think we only missed, I think, one or two slides looking at it. So I think it worked out for the best in the end. But that was brilliant. Thank you ever so much. So yes, we have a few questions from the audience, if that's okay with you.
Yeah, of course.
So just looking at sort of the gravitational waves, you mentioned things like neutron stars. Is there a way in which like this might look at the surface of neutron stars, whether they're actually spherical and smooth, or whether there might be sort of ridges or anything within those neutron stars? Is that something that this could be used for?
Yes, definitely. All the signals that we've picked up, all the gravitational waves that we've detected so far, have come from these pair events where pairs of objects are merging. Now, in studying ones involving neutron stars, we can try to tease out some information about how squishy neutron stars are. Now, they're not very squishy at all. They're extremely stiff objects, but they are able to be deformed slightly. And so we can try and see the hints of that deformation in the signals. But a better way to get a handle on how spherical a neutron star might be would be if we could pick up gravitational waves given off by a rapidly spinning neutron star that might wobble ever so slightly because it's not quite spherical. And that wobble could produce gravitational waves. And so people are actively hunting for signals like that. And we know that neutron stars are out there spinning very rapidly because we see those objects as pulsars. Pulsars are neutron stars which spin sometimes hundreds of times per second, and we know that they're out there. So we can try and pick up a faint kind of hum of gravitational waves coming from this wobbling neutron star. So that's an active area of research, and hopefully one day in the not too distant future we might actually pick that up. But so far we've only been able to place limits on how aspherical a neutron star is, and but that's only because we haven't been able to detect anything yet.
Fascinating. And then just, you were talking about, these have been used mostly for sort of pair events. Is there a potential that this could be sort of have a look at things like obviously string theory? Could this be used to sort of detect the presence of strings? Is that something that would be, strings interacting with each other, or would it be used in any way to look at that theory and prove some of the elements of string theory? Or is that too much of a stretch?
I think I'm kind of out of my depth going into much detail in string theory, to be quite honest with you. But I think if string theory made a prediction about a kind of object that might exist, or a way in which it could impact the makeup of an object that we might see in gravitational waves, then that might be a testable observation. But I don't suspect so, unless it obviously had a an impact further up the chain so that it changed the way that particles interact inside a neutron star. So I guess if studying the cores of neutron stars might have something to say about fundamental nuclear physics, and if string theory made any suggestion about how that might be drastically different, then maybe we would be able to see something like that.
And then another question we had was, do gravitational waves move at the speed of light?
Yes, they do. In Einstein's theory, they are predicted to exist and move at the speed of light. We've observed them in most cases from pairs of black holes merging, and the studies that we've done there are completely consistent with them moving at the speed of light. But the best observation was of a pair of neutron stars which merged. It's this signal down here, a pair of neutron stars which merged in 2017. And what we saw was the gravitational wave signal came, and then very shortly after there was something called a gamma ray burst. And that was the explosion caused by these neutron stars smashing together and tearing each other apart. And this thing happened hundreds of millions of light years away, and the gamma ray burst arrived less than 2 seconds after the gravitational wave peak happened. So from that, you can say, well, they've traveled such a huge distance, and the time that both of the gravitational waves and the gamma rays took was the same to within less than a couple of seconds. So basically, if gravitational waves aren't traveling at exactly the speed of light, they are very, very, very close to the speed of light, like as in 1 part in 10 to the power of 15. So basically, yes, they travel at the speed of light.
Is there a way to measure that down to that kind of level between, like, how they're measuring between the speed of light and, as you said, a very, very minuscule difference between that? Is there a way to measure that accurately?
Well, I mean, based on the fact that we saw both of those signals coming from the same event, and the offset was so small, given that the signals took hundreds of millions of years to get to us, and it was like a second and a half apart. If you make the safe assumption that both the gamma rays and the gravitational waves came from the same place at the same time, then that's how you get to that kind of accuracy.
Fantastic. Well, thank you so much, Andrew. That was a really, really interesting talk. And thank you so much for joining us tonight. We really appreciate you coming along and letting us know. So we've now reached towards almost the end of our evening tonight. We do have one more game, one more activity. So I'll ask Andrew and Chai if they wouldn't mind. Normally at the end of these events, we like to get our speakers involved as a thank you / slight torture for coming along to our events. So if I'd ask you both just to unmute and turn on your cameras, if that's okay with you both.
Sure.
So we always like to have, as I said, a sort of a bit of a game at the end. It's just to test, the mettle of our superb experts who come along to talk, and of course, show our appreciation by putting them through this. So I apologise to both of you initially, when you're both very good sports doing it. So thank you. So our game tonight, and I think, Andrew, you set this up beautifully by your mention of M87 and the photo there. So this is a variation on a game that we played when we were actually in the pub, called the Close-Up Challenge, which is subtitled "What the hell is that?" So basically, obviously, with the with the Event Horizon Telescope and the picture of the supermassive black hole at the center of M87, technology has come a long way. We've used some fantastic tools that have allowed us to see into the deep secrets of the universe. So what we've done is used another secret of the universe, Microsoft Paint, to zoom in on some famous space photos, and your job is to identify which of these space photos we have zoomed into by just one tiny square of that photo. So there are 5 questions. So you have 2 questions each, and then there is a final question for both of you as a tiebreaker of sorts if you get the first 2 right. So Chai, as you are our first speaker, would you like to go first? So our first photo is this. Can you identify, and I'll allow you some leeway here, what this photo is from this one square?
Sorry, John, your voice broke a little bit for me when you were explaining the question. So am I right that I'm going to identify from this photo some pixels that taken from the other one? Yeah.
Yes, so we took one pixel. We used the magic Microsoft Paint to zoom into one famous space photo, and I'd like you to try and identify it from this zoomed in picture. Can you see it? Okay.
Yeah, I'm looking around.
Any ideas?
I would pick the pixel that's down at the bottom middle.
Okay.
Reddish. I think that looks like it's some sort of human skin.
Okay. So what is the original photo? What do you think that it is? It's just one small piece of the bigger photo. What do you think the photo is showing? I'll give you some. You can be you can have some guesswork here. You don't have to be very specific.
Well, the original photo, if I remember, it's the outer part of the black hole that has the orange and the reddish color, and that's my best guess.
Okay.
Yes. Color-wise, they look similar.
So you think this one? Well, I'll show you. So this is the photo here. So this is photo number 1. This actually came from. This was a picture of the International Space Station, and this is the crew of the International Space Station in, I think it's November 2000. This was taken. Can you see that there?
All right.
So that was probably my explanation for that. So I apologize. This is starting you out. We should have had a good example to start this off. So
all right.
So I apologize for that. So Andrew, we'll move on to photo number 2. I feel like this one's slightly easier. Andrew, any ideas?
Yeah, I think that's the tire tread on the Mars rover. I don't know.
And you would be correct. No, you are absolutely correct. Well done. This is the tire tread on the Mars rover. There it is, waving at us. It's a beautiful photo. Fantastic. So, Andrew, you're currently in the lead with 1. Very impressive. Guy, I will come back to you for photo number 3. Now, this one, I think.
This is photo taken from the moon.
Yeah.
Well, let me get this one more time.
Go on.
From the space station, International Space Station.
Yep, you're correct. In orbit around the moon, it was the Earthrise photo that was taken, looking back at the Earth from the surface, well, orbiting the moon, which was right. So correct. Okay, so we are 1-1 going into photo 4. It's very exciting. Photo number 4. Okay, back to you, Andy. Any ideas about this one?
So, using a bit of astronomy knowledge, the thing in the middle is a star because it's got that spikiness to it. But the other objects must be like galaxies. I think so. This is probably like the Hubble Deep Field or something like that. Very
good. Yes, this is the Hubble Deep Field photo. Very, very good. Well done. Excellent. Okay, so Andrew, you are winning 2-1, but as I said, there is a tiebreaker at the end. So either this will draw things up and we'll leave on a dramatic tie, or Andrew, you will emerge as the champion. So photo number 5. This one's a bit hard. So I'll let you both have a little look and just have a little think. Okay, Chai, any ideas?
I guess this could be a photo of the Mars when before the lander touched down.
Oh, that's a good guess. Andrew, any guesses from you?
No. I mean, it's kind of like a skin hue, but I don't really.
But it's 2 squares.
It's got those squares on it, yeah.
Well,
yeah, but it could be seen some
I do
maybe
apologise for this one. This one is a bit of a trick. Go on, Andrew.
Maybe it's sort of part of like the mirror of the James Webb Space Telescope or something like that. It's like a reflective surface.
Those are both excellent guesses, but you were almost there with your first one, Andrew, because this is Buzz Aldrin's forehead. So
well, he's got very parallel wrinkles.
He does have, yes, surprisingly parallel wrinkles. He's a very like smooth foreheaded man, which is very strange, but I apologize. So I think we can say, Andrew, congratulations. You are a champion for your game. Chai, thank you so much for playing as well. You're both a really good support. Thank you very much.
Cheers. Thanks.
Thanks.
Okay, so we've now come to the end of our event. The last thing I wanted just to quickly say before we finish is that big congratulations to Thompson Space on Twitter, who was the winner of our beer award. We had an event, the last couple of events, we've had a competition to name an Astronomy on Tap related beer. The nomination from Thompson Space was an RPA, which is a Red Planet Ale. So congratulations to you. We will get in contact with you with your prize. And the next job for us is to figure out how we're going to use that beer name in the future. So if anybody works for Brewdog and has good connections, let us know. We'll pass it on, see if we can get it made. Lastly, just a huge thank you to our speakers again tonight, to Dr. Andrew Williamson, Yan-Chuan Cai, and to all the volunteers and for everybody who came to watch. We really appreciate it. Please do remember to subscribe to the YouTube channel, and you can also follow us down here on Twitter and on Facebook, if you can see that. But yeah, thank you so much for joining. We will see you again. Take care. Bye, everybody.